Hello, everyone. Thanks for sticking with us. And next, we're going to have Dhanya Sridhar. She's an assistant professor at Université of Montréal in computer science. And I've been working with her since she came aboard at Mila. She's working on causality, something that is clearly missing from the current state of the art. So let's hear her.
Thank you very much. That's the first time I've ever gotten applause before the talk even started. So thanks for kicking me off with such a warm welcome. Thanks very much for inviting me to the organizers. It's a pleasure to be here. It's my first ever times at Simons. And it's nice because I did my PhD not very far from here in Santa Cruz. So it's lovely to be back in California. I'm appreciating that. So indeed, today I'm going to talk about something called causal representation learning. And I'm just curious, so how many, if any, in the audience have heard this phrase before? Okay, that's like a big, big number. So that's great. Very happy to hear that. But nevertheless, I'm going to do quite a bit of introduction or tutorializing sort of at a hopefully interpretable, intuitive level. And so what we've been doing recently with my student Shruti, who's here, and you should chat with her, is trying to link these ideas from causality and machine learning to interpretability and steering of LLMs. And when I first started with this topic, these words like interpretability and steering were a bit opaque for me. And so we're going to just start the way I started learning with a very sort of concrete, simple example. So just to illustrate what do I mean when I talk about interpretability or what I am thinking of when I say steering, we'll take this very simple example of training transformers to do two-digit addition. Okay, and so here is a transformer on the left with the inputs 16 plus 25. And just to kind of get on the same page once again, what we mean when we think of these embeddings is that we have the token itself that gets embedded by the transformer and gets successively modified by layers and layers of multi-headed attention and MLP being added to the residual stream. Okay, and that gives us our final layer of embeddings for every single token. Okay, here's a computer program or simple little algorithm that we probably use when we solve this task. Okay, so you have your first number and its ones place digit. You have the tens place digit and the ones place digit. You've got your second number and you've got its tens place digit and ones place digit. You compute typically the carryover variable, and you would compute the outcome in the ones place and in the tens place in this particular way. And for concreteness, let's ask the question, if I wanted to perturb the carryover variable, right? For this particular example, I want to go in and intervene on the system and set it to 0. How will that change the behavior of the model? Obviously, this is the wrong answer to this problem, right? But this is the correct behavior under this particular intervention, according to this kind of causal model of doing two-digit addition. And now I may want to know, is there some place in the transformer I can intervene on to simulate this exact same behavior? So this is tantamount to asking, is there some place I can edit or make an edit such that I get the same exact behavior, such that the transformer also outputs 31 instead of 41? Okay, this is not obvious at all, because these kinds of concepts, these latent factors that we might use in causal models, these are going to be typically distributed across the dimensions of embeddings and across neurons in the MLP. Okay, so there's no reason why you should be able to do an axis-aligned perturbation in the transformer for some kind of concept. So the goal of the unsupervised interpretability pipeline, or unsupervised feature discovery, as it's sometimes called, is that we would like to learn some other basis, right? We would like to take our token embeddings and find some other basis in which these underlying concepts actually are disentangled. So maybe one dimension of our new basis that's here in red might represent this carryover variable. Another dimension, maybe the dimension number 1, represents the tens digit, the tens place of the first digit. And you can hope to map back, to mix back to your transformer embedding space. Yes?
Why do you put it to basis and not just features?
I'm being colloquial here. I just mean like we're going to try to find a different set of features that are disentangled. Okay, good. So how will this help solve the problem we initially laid out? So you can try to perform the intervention in this disentangled feature space. You can see what that intervention is going to look like in token embedding space using the decoding function. And now we would hope that if I copy that over to my last token, last layer embedding, then I will get the intended behavior, right? Now, just like the high-level model, the low-level model, the neural network, the transformer, also produces the output 31. Okay, so how is this being implemented currently, or it was as of months ago? We were borrowing ideas from compressive sensing, actually, this very old idea of dictionary learning, where the idea is to decompose a dense signal into a sparse sum of signals. Okay, so a sparse sum of signals. I do mean that because these kind of directions themselves don't have to be sparse themselves, but we would like to use just a sparse combination of them. Okay, so this idea comes from dictionary learning and compressive sensing, and how it was sort of implemented in interpretability research is by trying to learn an autoencoder. So we would try to learn some kind of linear-ish encoding function to take our embeddings, represent it in some kind of sparse, again, I'm going to say the word basis, in a sparse basis, and we will try to reconstruct our original input using a linear decoder. But we have a very, very crucial constraint to capture the sparse aspect of sparse dictionary learning, which is that the number of concepts I should be using to represent any given signal should be sparse. Okay? Okay, so this is the sort of objective, concretely. And this was sort of broadly adopted in the interpretability community around 2023. And notice that this all makes sense when concepts are actually represented linearly in our embeddings. Why might this be true? Well, there's a lot of old and new evidence to support this hypothesis. Back in 2013, when we were still doing Word2Vec style embeddings, there was evidence empirically that those kinds of models represented concepts in linear directions of embedding space. And more recently, there's theory work that says why maybe even next token prediction models also in their last layer represent concepts linearly. Okay, I can talk more about that later. I'm not going to get into that in this talk. But the key thing, right, is that if the concepts really are disentangled in this given model, then each column of our decoding function gives us a unique steering direction, right? I don't know which concept corresponds to decoder column number 0, 1, 2, and so forth, but it is a single concept that gets manipulated if your concepts truly are disentangled. Yeah.
Is that more or less a definition of the concepts being disentangled? Is that what it means to say they're disentangled, or is it? Well,
let's make what disentangled means a little bit more precise in a little bit. But for now, you can think of it more as an implication. Okay. Okay, so how has this been working, right? As I said, sparse autoencoders started appearing in ML papers, inspired by sparse dictionary learning. They gained popularity with Anthropic. They gained even more popularity such that, for example, Google DeepMind released a really, really big pre-trained sparse autoencoder for Gemma, made it open source. It was, starting to gain quite a bit of popularity. Then there were more research papers looking into sort of extensive and rigorous evaluations of sparse autoencoders, and there started to be mounting evidence that they did not seemingly discover or disentangle concepts in a way that would lead to useful steering or that would lead to useful concept detection. And it got to the point where Google DeepMind is now announcing that they're moving away from SAEs. And I can't help but think we'll be on to the next kind of hype in interpretability research. And I'm going to argue that there are these boom and bust cycles that we keep going through in interpretability and steering research that I think we can sort of guard against by considering unsupervised methods that have more guarantees, right? And what I'll say what I mean guarantees, but in loose terms, we're going to provably disentangle concepts. Okay. I saw a hand up.
DeepMind keeps mistiming that curve.
Yeah, maybe we could do some forecasting models as well. Okay, so disentangling and provably, how do we do these, right? How do we do this? So what's nice is there's been long-standing field called causal representation learning that's all about doing deep learning such that the features that you discover in your representations have some kind of intervenable semantics. These typically will correspond to the kind of concepts or factors that I would like to intervene on in isolation. Okay. And we'll set this all up. So, bear with me as I go through kind of simple examples, and then we'll be a bit more precise. I'll take a question, but only if it's a clarification question. If it's going to be open-ended, we'll wait until the end.
I guess I wanted to clarify what's the right way to think about these concepts? Because it seems like there's just, even in this addition problem, there's so many things I could think of as concepts here.
So I'm going to ask us to just hold on to this because I think as we make things a bit more precise, we can come up with a generative model interpretation to factors or concepts. But I think we'll come back to it at the end if it's not clear in the rest of the talk, okay? Okay, so let's actually take a simpler problem, or arguably a simpler problem. We're going to consider images, and we're going to consider learning encodings or embeddings of images. And these are going to be very, very simple images. I'm going to have balls. The only sort of dimensions along which these images are going to vary will be the balls will be in different places on the x-axis, and they're going to vary in color. So there are only really two factors of variation here. And let's say I have supervision from text. And so I'm going to have little captions that tell me, where the ball is in the image. And just for a concrete example, I'm going to consider the sort of clip style objective. Okay, but I want to be very, very clear here that everything that I'm going to talk about, this applies for a really wide variety of representation learning objectives, including autoencoding, including things like VAE style, modeling the log likelihood of the observations. So this is just one example, just to be very concrete. So let's say we're going to do something clip style, where let's say I have a way to encode my captions. And let's just say that's fixed for now. And I would like to learn an encoding function. I'd like to learn an embedding of my objects. I'd like to learn some set of features such that I can linearly map back to my text encodings. Okay, so that's we're going to set that up as the objective. Any questions? Okay, good. So I've illustrated one solution here that will work, right? This particular axes are just a rotation of this set of features, so they will be linearly related. And it just so happened to be a very nice choice of basis. Why? Well, the axes, I should say, of this basis align with the kinds of things we would like to intervene on in isolation, right? So, even if in my images, every time I got to a new image, both the color and the position of the ball changed, what I would like to do after I train a model might be to independently, in isolation, manipulate these concepts. And in this particular nice basis, all I have to do is translate along one axis only. And when I do that, only one thing is going to change. In this case, the color. Okay, the question is going to be, am I guaranteed to learn that very nice basis with my objective? And a lot of you might be already seeing this already, but no, right? Because I can perform any rotation and I can minimize the loss equally well. But this particular basis is, I think you can't really see the nice colors I have on the back of this rotation, but you can see that now if I want to change the color of the ball only in isolation, I'm actually going to have to move in this diagonal direction in my new basis, right? Where previously all I had to do was perturb a single axis. Now I'm going to have to find this special vector that allows me to change the color. So we can see this a bit more clearly. Now, if I did some kind of axis-aligned change, I would hope that this changes very, minimal concepts in my image, but multiple things will change. The ball will become gray and it will move to the center at the same time. Is this so bad? I mean, you could, in theory, try to learn that direction of change using labeled examples, but this is the key, right? Like now we're suddenly back to a problem where we need more labeled data in order to do some kind of steering. So what can we do with just unsupervised learning? Do we have any hope at being able to learn those nice disentangled concepts? Okay, so I'm very deliberately being cheeky on the slide by trying to just overwhelm with a ton of references. I'm not intending you to kind of read through all of them, but the point is this is a very, very, very long standing area of literature, starting as early as actually 1990s with linear ICA. Unfortunately, the first citation I have is from 2016. But this is a very long line of work on how to design objectives and representation learning that are identifiable. That is, if you minimize them, you can guarantee that all the solutions that are part of the set of the minima will have some very nice interpretable property. And I'm going to kind of talk through at a very high level just one of them, just to illustrate how these methods work and how they go. Okay, and then I'll talk about one of our papers that now maps this idea back to interpretability. Okay, so this particular idea from CRL is at a very high level all about using weak supervision. Okay, and what is weak supervision? We're going to have paired samples rather than just single observations. And in this particular example, you have a bunch of balls. And a nice way to represent these images might be to encode the XY position of each ball and also its hue. And here's a bunch of different perturbations you could do, okay, with varying levels of sparsity. So maybe perturbation number 1 is just going to move the green ball. Perturbation number 2 is going to move the blue ball, so on and so forth. You have denser perturbations that are going to start moving the objects both along the X and Y axis. You can have even more dense perturbations that move multiple balls at the same time along both axes, right? So you can have this sort of rich set of perturbations that vary in terms of how sparse or how dense they are. And if you have these kinds of paired observations, remember the key here is that we have, counterfactual samples where you have your original input and a perturbed version of it. We can use this to train our encoder. And in particular, let's say you actually had sparse perturbations, then you could train an encoder to make sure that the encoding of an image and its counterfactual twin don't vary by too many dimensions. Okay, so you can make sure that f of x and f of x tilde, where f of x tilde is the embedding of the counterfactual, you can force the difference between these two embeddings to be sparse. Okay. Why? What does that do? What is the sparsity regularization in differences? Remember, what does this do? Well, we can prove theoretically, especially when the shifts are one sparse, that you can in fact show that all of the solutions learned by this particular objective, right, the minima, are going to be z hat, which is f hat of x, such that it's related to the ground truth up to a permutation and scaling. Okay, so in other words, you can just think that there's a one-to-one alignment between the ground truth representation, which when I say ground truth, I was talking about that nice basis in which all of the concepts are independently intervenable, and the solutions found by this particular objective. Okay, so this is concretely what we mean by identifiability, that there is this kind of permutation, scaling, indeterminacy that's left, but that's all that's left. Let me pause here. Yes.
Weak supervision, but it feels like it might be a bit stronger than that because it's isolating an individual object in your environment and saying, I've moved this object, right? So
you're totally fair in saying that. I mean, so I think this is one of those like you know, naming conventions can be very misleading, and you're right. Weak supervision is highly debatable because I think it's trying to draw the contrast that you're not directly supervising and, for example, saying, okay, for this image, it's represented in terms of this, and this measurement. Rather, all you're kind of supervising is with regards to what are the kinds of, you know, axis aligned changes you have. But indeed, I think that's a very good point. Yeah.
So how about getting the same kind of information from the textual representation of the student's work? Is our change in color
that is a fantastic question. I suspect people are probably working on this. I've heard rumblings around Mila that people are trying to do like sparse clip and things like this. So I wouldn't be surprised if this is happening. But okay, so that's one kind of idea, right? We're going to sort of port that over to interpretability. So again, what were we doing? We were trying to take sort of rotated embeddings of images, and we were trying to unmix them so that now my axes are going to correspond to the kinds of interventions I would naturally want to make anyway. I'm going to try to do the same thing now to my token embeddings, right? I'm going to try to find a representation such that the latent features that I learn are going to be the kinds of concepts I want to steer. Okay. So I said something about empirical findings recently that, you know, sparse autoencoders were not necessarily meeting their promise. So that paper is very nice. It's called Axbench. And they did a sort of fairly extensive set of evaluations, including human evaluations where they would steer, generate completions, and then get humans to score them in a particular way. And they did a lot of other kinds of evaluation such that if your model was actually disentangled, it should be somewhere over here. Okay, so I'm not going to go into the paper, but say that the evaluations that they did had this nice property that it was sort of a testable implication of disentanglement. If you had disentanglement, you should do well on the tasks that they set up. And we see that, you know, SAEs, ignore this because that used a little bit of supervision. It sits somewhere over here, which is not good. So that's kind of, you know, leading to this observation that maybe SAEs don't actually disentangle concepts. So the question is, do we actually end up with entangled features like our rotated basis earlier? Right? Is that what is happening with SAEs? I'll get back to these experiments later, but we did our own sort of studies as well using a different set of tasks which were different natural language data sets where there are some natural language concepts that are varying. And we looked at these examples, Z and Z tilde. Again, these are embeddings, remember, where Z tilde is an embedding that derives from a single concept shift in the prompts themselves. And we tried taking each column of the Llama scope open source decoder to steer Z and see if you get pretty close to Z tilde. You have to search over all columns, remember, because there is still this permutation and determinacy that we can't do anything about. And our findings were a little bit more promising or favorable. We found that, cosine similarity is not bad in some of these data sets, but when it fails, it kind of fails catastrophically sometimes. This particular data set involved concepts that were languages, so that's something interesting here, which lends to this kind of further hypothesis that indeed maybe there's something about SAEs that doesn't allow them to disentangle concepts, despite the fact that there's this sparsity regularization, right? And this is a bit strange. Like if you have sparsity regularization, as we saw earlier, this typically led to disentangled features. Intuitively, something is going wrong. What is that? So issue number one, right? This is all about the devil sort of being in the details here. Issue number one, some concepts may not at all be learnable. So what do I mean by that? Okay. We have way more concepts than we have dimensions of embeddings. So, we can have examples where maybe there's sort of one activation, C1, a different activation, C2, right? So these are two different latent codes that represents the kinds of concepts you may have in a text, and they may map to the exact same embedding, the exact same, let's say, Llama embedding. Now we're trying to actually invert the data generating process, right? We're trying to go from Z to C. This is actually a failure of injectivity, right? You have two different inputs and map to the same output. So now if you want to go from output back to input, you wouldn't even know how, right? Here, like because of this lack of injectivity, disentangling is not even a well-posed problem. So that's issue number one. Issue number two has to do about lack of data diversity. So let me give you kind of a concrete example. So if you lack examples that capture only a single concept, let's say all of your examples that you have, they actually are activated by many, many, many concepts, then there are going to be a bunch of spurious solutions, a bunch of entangled encoding functions that also minimize the regularizer, right? We essentially lose, we strip the L1 penalty of its power to favor disentangled solutions above all else. And this is not actually surprising. We found this in our paper about sparse decoding. And this is sort of a well-known idea even for kind of algorithms that are more like sparse dictionary learning, where for this to work, you need to have some kinds of anchors, we call them, some features that require being described only in terms of a single concept. If you have this kind of actual sparsity in representation, then the L1 regularizer actually is going to select disentangled representations above all else. Yes?
Are we still in this weak supervision paired example setting? Is that where the single concept variations come in?
So we're going to leave that behind. We'll come back to it in a second. But for now, this is about just standard sparse autoencoders, where we don't have weak supervision. So we have this, right? We're going to try to take our token embeddings for a big corpus of token embeddings, and we're going to try to learn some encoding function that sparsely represents each token embedding.
We should let go of that like ball versus location, because there a single concept would be just a ball or just a location with nothing else.
Exactly. So we'll come back. Well, we will come back to that example, or we'll come back to the weak supervision case. But for now, we're momentarily back at SAE land. Yes.
Very related to that question. If we don't have the pairs, then how do we ever have just a single concept?
I mean, that is a philosophical question, but the hope with, I mean, that's exactly the point here, right? We showed that if you wanted to actually use sparse decoding or sparse encoding as an objective to get identifiable representations, you do need these anchor features that depend on a single concept. If you don't have this, you don't get identifiability. If that's the assumption that you think makes sense for your data, there's no reason to not use it, but you can argue that it's indefensible, in which case, indeed, we need something else. Okay, so we were motivated by these failures of sparse autoencoders, or these putative failures of sparse autoencoders. And we're going to go back to the weak supervision idea now, where it's going to be changes that are sparse, not representations themselves. And we have a method called sparse shift autoencoders that use multi-concept shift data. Okay, and that's sort of one of the contributions here, and I'll go into detail what this is. This was led by my fantastic PhD student, Shruti, who's here. So I encourage you to go say hi to her and ask her all your difficult questions. This is on archive. Okay, so let's start by saying, what are multi-concept shifts? Okay, here's a little kind of data generating process that we're gonna step through. To get multi-concept shift data sets, what we're gonna do is, first, we're going to sample some set of concept activations, some latent code in terms of concepts. Okay, so that's this over here that is drawn from P of C. Then, and notice I have a bunch of indices associated with this vector. Then I'm going to sample some subset of positions. Okay, so I might sample position 1 and position 4 from P of capital S, where capital S is going to index into subsets. Now, given my subset that I've chosen, I'm going to sample some vector, some shift vector delta. Okay, this tells me how much I want to change concept number 1 and how much I want to change concept number 4. Everything else is going to stay the same. Okay, I will apply delta C to the concept code that I drew, and I will get C tilde. After I've done this, there's some unknown mixing function that gives me texts from these concepts. Okay, I'm not going to assume anything about this generative function. I'm just going to ignore that. All I know is that I'm going to get X and some X tilde that are derived from C and C tilde correspondingly. Then I'm going to go and fetch their embeddings. So for example, I might go to the token embedding above the last token in the last layer. Right? That can be my notion of embedding for X. And I'm going to get Z and correspondingly an embedding for Z tilde. Right? So now I've just represented the difference between these two texts, but now in embedding space. And then I'm going to compute their difference, right? And I'll call this delta Z. And notice, this is the key thing, right? In my concept representation space, the differences were sparse. For example, delta C over here, right, has a lot of zeros in it and is only active in, say, coordinate number 1 and 4, because those are the concepts we're changing. Whatever is sparse in concept space does not have to be sparse in representation space. Here, we have a difference vector that's very dense. Okay, so we've lost that nice sparsity when we've moved from our nice concept space to the space of LLMs, because these concepts are entangled by LLMs. That's exactly what we have to solve, right? Let me pause here just to kind of ask or take any questions about what is a multi-concept shift. Okay, and let's just say as we're doing this, like where all the variability is, right? You can sample different sets of concepts that you want to change. For every single example, you're going to sample a different set of concepts you want to change, which means that some shifts naturally, some naturally occurring examples will differ by a single concept. Some will differ by 5, right? So you'll get this variability in terms of sparse to dense shifts. Yes?
So each concept is associated with a dense vector?
Each concept is going to be associated with a dense vector in embedding space. Yes.
And so, and then we just add them up to get whatever is going to be represented by a document. How are they combined to represent the mixture of that concept? The set of concepts.
Okay, good. So let's maybe just say one more time what. So there is this mixing function that we're not going to define that allows us to go from concepts to some mixture of these concepts, right? Or rather, we're going to observe some embedding that it has mixed up all these different concepts. And the idea is going to be that we have some embedding function f of x that is going to represent some kind of mixed set of concepts, and now we want to unmix them. Question?
Yeah, I think I missed what's on the left. Like, are these activations earlier in the network, or these are some pre-specified?
No. This is the data generating process. This is how the data is being. This is how the texts are coming to us.
Okay, so that's hidden. You don't know anything about that.
Yes. So, and this is like this is kind of, CRL very much adopts sort of a generative modeling perspective that's not at all kind of unfamiliar in probabilistic modeling, or if you work with variational autoencoders, you'll be used to seeing these kinds of latent variable models. The key thing that makes this different from standard CRLs, a lot of representation learning makes a lot of assumptions about the generative process, the generative function. Here, we are not going to make too many assumptions, or really any. Okay. Yes?
This sparse vector here, why does it have the same number of dimensions as the other Cs? So
because another way to think about this is you have C and C tilde, right? And this is capturing the difference between those two vectors. So this lives in the same space as the other two.
oh,
Okay. There's a couple caveats I want to make very precise at this stage. So fact number 1, right? These are not single concept shift data. These are not contrastive pairs that people typically use to learn steering vectors, right? If you had pairs that varied only by a single concept, you knew what that concept was, you can simply use those contrastive pairs. You can compare their embeddings and get the steering direction for the concept, right? That's what's typically done in supervised steering. That is not what this data is, right? This is strictly more general in the sense that you're going to have some pairs that vary by a single concept. You don't know what that single concept is. You'll have some pairs that vary by many concepts. You have this kind of variability across how much variation there is between your contrastive pairs. Okay, so one example that we give is, for example, you can use our method on something like synthetic contrastive pairs that are generated via LLMs. So for example, when you ask LLMs to take a prompt and then hold everything fixed but vary a single aspect of that prompt, I mean, maybe it generates perfect counterfactuals, but in all likelihood it does not, right? It may vary multiple things. And so, for example, using this multi-concept shift paradigm, we may be able to accommodate even data like this, right? Rather than having to have perfect, very, very clean single concept shift data sets, we can start leveraging much more cheap to obtain data sets where there's a variety in the number of concepts that are shifted between pairs. Any questions about what kind of data we have? Yes.
Clarification related to the last question. It seems like we do need to pre-specify the concepts we want to learn, because that's going to allow us to generate these pairs.
No. I think there's like a gap here, right? Like you have data, right? If you are willing to accept that this is an adequate data generating process to explain the data that you have, then you should proceed with, well, you should trust the guarantees of our method. You do not need to generate the data using this machinery yourself. If let me kind of ask, is everybody else generally pretty good at this stage? Okay, we can come back to this after the talk, but okay, good. Yeah.
Maybe if you like, say CFAR 10, does that data set fall under the category of things you would argue?
We have contrastive pairs in CFAR 10? I don't think so, right?
Yeah.
Probably not. I was thinking more kind of text-based contrastive pairs here. So sort of in this example that we gave, I wouldn't envision something, and maybe you can even use like a vision language model here, but like maybe you can ask Stable Diffusion to take a CFAR 10 image and then give you an image where the object, the semantic category is exactly the same, but the style is a little different. Yeah.
Maybe you could use consecutive frames from the movie.
Thank you. That's perfect. That's the stuff that I was talking about earlier from CRL with weak perturbations. That's exactly what they argue you should use, is like consecutive frames of a video, because naturally occurring shifts are typically sparse. Yeah, good. Okay, so what does this multi-concept shift data set solve? Well, we formalize in the paper conditions on the way that you should sample your indices and the way that you should sample your change vectors delta to get the sufficient variability that we need for sparsity regularization to be an adequate objective function for identifiability. And then how do we solve that question of unmeasurable concepts, that non-injectivity? Well, these concepts that you can't measure the differences in embedding space anyway, they're going to get canceled out when we consider shifts. Okay, so the unmeasurable concepts, the things that you cannot sort of have any observable implications for in embeddings anyway, they're going to get canceled out when you consider shifts. And the key detail here is we're going to restrict ourselves. We're not going to claim anything about recovering every single concept or disentangling every single concept. We'll only restrict ourselves, we'll only care about disentangling the concepts that vary within a particular multi-concept shift data set. Okay, so what are sparse shift autoencoders? I talked about the generative process here. It's a very similar idea to sparse autoencoders, except we're going to take as input these shifts represented in embedding space. We're going to learn a linear function to unmix these shifts into concept space. So you're going to try to predict for every single pair of examples, you're trying to guess which are the concepts that changed. I mean, really, you're trying to guess how many concepts changed. And with this guess, you're going to try to linearly decode and go back to embedding space. So again, we said this earlier, right? But the key thing here is we're not trying to find a basis like SAEs do. We're not trying to find a basis where the concepts used for a particular example are sparse, but rather where the interventions are sparse. Going back to the sort of weak supervision example from CRL. So the objective is here to be concrete. So we're going to minimize reconstruction error like before, like SAEs also do. And we're going to penalize, you see the L0 norm here, but in practice, when we do this constrained optimization, we'll use L1. We're going to penalize we're going to constrain rather, the sparsity that we're going to guess when we guess our shifts, when we try to guess the number of concepts that are used for every single contrastive pair. We're going to constrain that L0 norm to be less than some value beta. Okay, and what beta is exactly correct is a little bit special, and I can tell you more about this after the talk during the break. But the idea is that there's some kind of sparsity regularization that we perform. And because of the sufficient variability that I mentioned and the fact that now we limit ourselves to the concepts that actually vary, we can estimate the concept shifts delta C and the linear mixing function D up to that permutation and scaling indeterminacy that I wanted. Yeah.
So the theorem statement is about L1 or L0?
It's about L0, but in practice, we use L1, yeah. Okay, so again, like sparse autoencoders,
So how can you make hypothesis in this scenario? Because we have the case of multiple hypothesis testing, right? We have multiple hypotheses about the columns of the matrix. How can you make sure that the directions that you find are statistically significant?
So maybe I'll explain what the experimental protocol is, but I mean, I'm going to interpret your question more as being like, you still have indeterminacy after permutation. How do you know which column of your decoder corresponds to which concept? Is that how you would want to interpret this?
I also want to know if any of the columns are statistically significant with respect to corresponding to a column, because you might find some columns that are directionally represented, but they are not significant. We can talk.
Okay, so let me say this, right? There's a scaling indeterminacy. So all we can say is that the columns of the decoding matrix are going to be parallel to the steering directions, right? That means that if you actually want to shift your concept, you may have to apply the steering vector with a really, really high magnitude. That's something that we have to still sort of experiment with at evaluation time and figure out. But if this disentanglement holds, and now we've made precise what it means to be disentangled, you have to have this equivalence to the ground truth up to permutation and scaling. What we can say is that the columns of the decoding matrix are going to be parallel. Right? Each column is going to correspond to one steering direction, or is going to be parallel to one steering direction. Yes.
Is the theorem about the global optimum of the L0 problem, or of a solution you actually find in the local optimum?
It's about the global optimum. Yeah. This is a great question again, because this flavor of identifiability results, it really is about what happens in infinite data context. It's really about like, here is some distribution you have access to. What are all the inferences you can make from this distribution? In principle, in practice, you're right. Like what happens with our actual optimizer may find a very different solution. But in some sense, causality really likes these kinds of results because it tells you if this distribution doesn't even allow you to get the answer you want, you shouldn't even continue with estimation. It's hopeless. Okay, so we did some evaluations with Llama 3.1 embeddings, and what did we do? It's what we said before, right? It's this, we have access to single concept shifts at test time, and we're gonna see how well one of the columns of our decoder can predict the steered embeddings well. Okay, so we still have to do the search, and there's a bunch of data sets at the bottom here that me or Shruti can talk about with you during break, but the key thing to notice is that at training time for sparse autoencoders or sparse shift autoencoders, sorry, we have multi-concept shift data sets. We don't train them on single concept shifts, but we evaluate them on single concept shifts. The thing that we find here, there's a lot of other methods against which SSAEs perform much better. There's a bunch of these methods that use either training data like contrastive pairs in order to learn steering directions, or don't do sparsity regularization. What we found with regards to SAEs is that our method performs very comparably, like very competitively with SAEs, and where SAEs had previously done quite badly, we do significantly better. We sort of maintain the advantage. There's still a lot more work for us to do here in terms of like scaling this up, evaluating on benchmarks like Axbench, and actually generating some completions to maybe see how well the completions look. But for now, the key takeaway is that they're competitive with SAEs and significantly better where previously SAEs had not worked. Okay, so I'm very happy to say I'm almost done, and so we've hopefully meant a lot of time for questions. And I'm not going to end with any hot takes. I would rather kind of calm all our nervous systems down, and we're going to end with a forest, very beautiful forest. I took this picture myself. And I think why, well, I want to kind of see the forest through the trees for a second, right? What is the sort of summary of this talk? I would like to kind of bridge the link between what I work on or have worked on for a while, causal representation learning, and problems that occur in interpretability and steering of LLMs, which clearly link to controlling their behavior to be aligned with human goals. CRL is this field that unifies a lot of different strategies for kind of provable recovery of nice representations, where nice means the independent components are themselves intervenable in isolation. One thing that I didn't talk about today, but there's a lot of work in CRL already on both learning these causal features, these causal variables, and causal models over them at the same time, right? Up to some, I'll just say for now loosely, not so bad indeterminacies. And the last couple of days, I've been very sort of buoyed to hear there's a lot of interest in discovering causal models, not just for steering, but to help with planning and reasoning. And I'd love to chat more about how CRL could actually offer a very nice starting point to some of these problems that others have discussed as well. So with that, thank you for your patience and for listening, and I'll be happy to take any questions. Yes.
Very, very nice talk. Thank you so much. It seems like a lot of the uses of original SAEs were done fully unsupervised, whereas here you're getting a win, but you have to have this sparse shift data, right? So how big a limitation do you think that is? Like, what use cases do you see yourself being able to recover easily? Which ones are more out of reach?
Yeah, I think that's a great question. So I think you're right that there is this sort of no free lunch with identifiability, where you get identifiability by paying a bit of a price in some sense, and either you can add inductive biases or constraints on the generative process itself, which is done. Sometimes you can limit your mixing function. This already gives you results. Or you can get some kind of non-IID data. So I think what I'm maybe hopeful about is that there's been a lot of work that really focuses on using very, very nice contrastive pairs for steering. And so I'd be really kind of excited to press on this, like, what if we can use LLMs to do sort of synthetic counterfactual examples generation, which previously didn't make sense because they weren't generating faithful counterfactuals, but now you don't need that. You can accommodate some amount of, more than one concept is actually being perturbed. So that would probably be someplace I would start. Both hands went up at the same time.
Okay. Yeah, my question is about issue 1, because you said that injectivity was a problem for sparse autoencoders. Yeah. And so with SSAEs, and there is an injectivity problem as well. And so you...
No. So what happens is all those concepts that were non-injective with respect to our token embeddings, they get canceled out when you consider the shifts. And so indeed, like in our actual theory, what we have to do is we do have to make an assumption now that like the mapping from the concepts that actually are changing in your data set to token embeddings are injective. But the point is, we think that is much more of a, a defensible position. Siva, and then Jeffrey.
Yeah. Great work, by the way.
Yes.
So this seems like a separate component from the main network, right? You have your transformer language model, like you can build whatever it is.
Yeah.
then you're building a separate model where you can tease out what these causal representations are.
Yeah.
But do you think like you can combine both of these and actually have
100%. Great question. So there was a very, very nice recent paper that would learn sparse features using SAEs, and then they did some kind of circuit discovery. And they found that they were finding much more sparse and interpretable circuits than before. So there's an opportunity to kind of combine these two paradigms where you kind of unmix the concepts that are, or the embeddings learned by transformers, and in that unmixed space that's much more interpretable, you can do things like simulate perturbations and interventions, or learn features, for example, and then map back to the transformer using the decoding function.
How out of reach is it L1 version of your theorem? Because the original compressed sensing, the results are for L1, and kind of the rest of your thing is L is convex. So can that be follow on?
Yeah, you're right. You're absolutely right about compressive sensing. That's a really, really good question. I don't have an answer for you right now. I think I've got to think about it. Maybe Shruti will also have some thoughts. Yes, Yashua.
My question is a little bit off and philosophical.
Great.
So, why are we trying to do this? And I mean, Anthropic's motivation is because we don't trust those nets in the language space. So we're trying to read something that isn't visible on the output side.
Yeah.
But if we focus on the question you asked about disentangling concepts, there's already a space for that. It's called
language. Yeah.
So it seems to me that we have the disentangling. The problem is the deception or the fact that language will be used in ways that don't correspond to our, the meaning we would, we expect, because it is lying, let's say.
Totally. Yeah. So I do agree with you. I think one thing, though, I think it would be, interesting to take the question of language as latent variables very seriously and ask, nevertheless, is there some indeterminacies that we may end up having to face where maybe it's not so much that you want to like disentangle the meaning of every single token. As you said, they're already disentangled, but maybe the tools of identifiability theory can help us ask, like, even if you have multiple candidate theories expressed in terms of little sentences, is there some kind of inductive bias we can place to get the best theory that explains this data? I mean, like simplicity is one, but there may be things in terms of sparse changes and these kinds of ideas.
Yeah, hi. So you do a nice job on contrasting this with sparse autoencoders.
Yeah.
But I was wondering if you could help me like contrast this with more supervised methods like concept bottleneck models or.
So I'm not that familiar with concept bottleneck models, so I can read the paper and get back to you, but
like a whole field of research, I guess.
So I mean the supervised methods, pardon?
It's like a whole field of research. It's not a single paper, but sure.
I mean, okay. Then I have to stand here and admit I'm not that familiar with that field of research. Okay. But the supervised methods I can speak to would be, if you have positive examples of the kinds of completions you want, or you've positive examples of prompts that differ by a single concept, you can use things like difference in mean embeddings to get steering directions. What I can say here is that the goal is not to kind of beat those methods, right? Is to offer an alternative that uses much cheaper to obtain data.
I'm going to suggest we push other questions to the break. We only have another 15 minutes.
Great.
So see you in 15 minutes. That's
perfect.
Thanks, So I'll just make a couple of points just on logistics. So a couple of updates. One, I made it